Welcome to homework.
Our question wants us to consider a linear accelerator which produces a pulsed beam of electrons with 500 pulses per second, that's N. The pulse current I is 0.5 amps, and the pulse duration, delta T, is 0.1 microseconds, or 0.1 times 10 to the minus 6 seconds. For part A, it wants to know how many electrons are accelerated per pulse. Okay, so we can do that first, part A, using the fact that the charge Q that flows past any cross section of the beam in a time delta T is given by Q is equal to IT. So we can write that out. Q is equal to I delta T. Okay. And the number of electrons N is equal to Q over E. So N is equal to Q over E. So therefore, N is equal to I times delta T over E, where E is just the charge for electron. It's 1.6 times 10 to the minus 19 coulombs. So you plug that in for E as well as the values for I and delta T. This comes out to be 3.1 times 10 to the 11 as the number of electrons. We can box that in as our solution for A. Part B says, what is the average current for a machine operating at the number of pulses N is equal to 500 pulses per second if the electrons are accelerated to an energy of, so that's all we have to do for part B. So I'll write this here. Okay, so over a long time T, the total charge Q is equal to, total charge, we're going to call it capital Q, is equal to N times lowercase q times T. Okay, well, I average, so the average current is equal to N times Q. So Q here is equal to I times delta T. So this is N times I times delta T as previously established. So plugging those values in, this gives you 2.5 times 10 to the minus 5 amperes. And that's the average current, and we can box that in as our solution for part B. Now part C says to figure out the average power if the electrons are accelerated to an energy of 50 MeV, so that's 50 times 10 to the 6 volts. So this is part C. So P average then is going to, this is I average, this is capital A. Okay, so P average then is going to be equal to I average, which we just found, multiplied by the potential V, which is 50 times 10 to the 6 volts. So you plug that in, and this comes out to equal 1,250 watts. We can box that in as our solution. Now part D, we'll just do that right here so we don't have to open up a new page. It asks to calculate the maximum. So maximum is going to be P is equal to I times V, which is going to be equal to 2.5 times 10 to the 7 watts. This is times 10 to the 7, not times 7. We can box that in as our solution to part D.